Hello and welcome. This is Dr. Khurram Naveed, and today we are going to implement binary multiplication using behavioral modeling. So in this tutorial, we will implement binary multiplication on this Xilinx software, which you can see on the screen, and we will use Verilog HDL, which we have been using in our throughout our tutorials. So in the previous tutorials, we learned how to make binary multiplier using gate level Verilog HDL, where we used a lot of logical gates, and we also realized that as the number of bits in the inputs increase, the circuit of binary multiplication became more and more complex. But today we will see we can implement this complex binary multiplication operation in a few lines of Verilog HDL. So in order to do that, we first need to see how uh, binary multiplication works. So here we can see multiplication of these two binary numbers, where this one is the multiplicand and this one is the multiplier. So so in binary multiplication, we multiply each bit of the binary multiplier with the multiplicand. So apart from this multiplication with individual bits of binary multiplier, we also perform these shift operations, right? So let's see how this whole process works. So in this case, we see that the first bit of the binary multiplier is 1. So, so when we multiply this whole number by 1, it essentially means we are copying this number and pasting it in the first row. So since the index of this digit is 0, so this means there are going to be no shifts. But when we move to the next digit, we see that the index of this digit is 1, and hence we have this one shift operation. So first we multiply this 0 with this multiplicand, which leads to all zeros, as you can see here, and this location of this uh, bit, or the index of this bit, dictates that we shift this result uh, by 1, which essentially means this we have 0 here, right? So and then we move to the next bit. So here we again have a 0, and when we multiply it by 0, multiply this multiplicand by 0, we again get all zeros. But this time, since the index of this digit is 2, we will have two shift operations, which means we will have two zeros here, 0 here and a 0 here, which means essentially instead of being a 5-bit result, it would be a 7-bit result. And when we multiply this multiplicand by the final bit of the multiplier, which is 1, we again copy this whole number, the final row. The index of this final bit is 3, so we have these 3 shift operations. And we are essentially adding uh, these shifted versions of these binary multiplicand, right? So so let's begin with this coding process. So I've already made this project file, which you can make this project by going to this new project and then clicking here and then writing the name, which I have already done. But you can specify your own name, your directory, and then you can click here and add new source, and then you can select this Verilog module, name your file, and that's it. That will lead you to this file. So since I've already added it, so I will open it. So first let's see how this shift operation works, because until now in our tutorials we have used most of the tools in behavioral modeling, but we have still not used this shift operation, right? So let's first see how this works. So let's specify inputs and outputs first. So this product is our output, and this multiplier and multiplicand are our inputs, right? So now let's specify that these are inputs. So we assume that we have two 4-bit inputs which we want to multiply with each other. So the number of bits in output are equal to the sum of the number of bits in multiplier and number of bits in the multiplicand. So since multiplier and multiplicand are both 4-bit numbers, this means so the product is 8-bit uh, uh, binary number. So let's specify that. Now let's see how we can perform this shift operation. So we perform this shift operation using this operator. So on the right side of this operator, we have the number of shifts. Let's say we want to shift by 1, or we want one shift operation in multiplicand. And we want to place the result of this shift in the product variable. So let's just use this assign operator. So now what we are doing, we are shifting the input, the multiplicand input by 1 and place the result in the product, right? So let's just save this. Let's add a test bench. So let's select this Verilog test fixture, name it TB underscore multiplier, and now click next. Yes, so I already made a file with the same name, so I'm replacing it. Click next, because here you need to link your module with the test bench. So your module is multiplier, so you select this module, click next, finish. Right, so this is our test bench. So in this case we are only checking whether we are able to perform the shift operation or not, and we are shifting this multiplicand input. So let's specify this 4-bit number here, then let's save this uh, and run its behavioral check. And now select this one and then run its behavioral check. So both are fine. Now let's move to simulation. So as you can see, so this one is the multiplicand, and here it is, you can see there is a shift of in fact the right shift of 1. So you can see this 0 which is not part of this 1 0 1 1, this multiplicand, but here you can see we have a 0 and then this 1 0 1 1. So this means so this is how we can shift a binary number and then store the result in another variable, right? So once we have done this, so now implementation of a binary multiplication uh, is now very simple. So since we are trying to implement a behavioral model, so let's use this always block first, and so in this always block we use inputs as the condition of execution of this block. So let's write both of these inputs here. and write this OR operator. So this means whenever there is a change in any of these inputs, so this block will be executed. So now let's write begin, which means that we want to begin this block, and here we specify the end. Right. So now so whenever we are implementing any logical circuit using behavioral modeling or this always block, we specify this output as reg type. So it is important that we specify this output as reg type. So write this product. This is here we specify that product is output, and next we specify that this output is of type reg or register for that matter. Right, so this is because we want to change the values of this product during the execution of this program. Okay, so now let's specify that product is equal to 0 in the start of the multiplication operation, and we do not use this assign statement in the always block. So in multiplication, as we have already discussed, that we add shifted versions of the multiplicand, but only when we have ones in the multiplier, where the number of shifts are determined based on the location of the one in the multiplier, right? So for example, in this case where this one is at location 0 of the multiplier, there will be no shifts in the multiplicand, so as you can see here. But in this case, since this one is at location 3, so there will be 3 number of shifts in the multiplicand. So effectively we are adding these two numbers, where this one is exactly the multiplicand and this one is a shifted version of the multiplicand, where these plus signs means we have 0 here. So these are 3 zeros, right? So 0, 0 and 0, which denote the right shift, right? So this means we need to first be able to detect a 1 in the multiplier. So in this case, since we know we have two 4-bit inputs, so multiplier is also 4 bits. So let's use this if statement to check whether we have a 1 uh, in this multiplier. Right, so first we compare its 0th bit with 0. So if this is true, sorry, in fact we should compare it with 1. So it's because we want to detect 1. So first we compare the 0th bit of this multiplier with 1. So if this bit is 1, it means we need to shift this uh, this multiplicand 0 time, like there are going to be no shifts, right? So in this case we will add the shifted version in the product, as you can see here. So we add this in the product, which is initially 0, right? And then we store the result of this operation in the product variable, and then we compare the next bit of multiplier with 1 to check whether we have a 1 there or not. So we compare the the this bit in multiplier at location 1 with 1, and if this is also 1, means now we need to shift the multiplicand by 1 and add it in the product, which in now contains an addition from the previous operation, right? Okay, so subsequently we compare the bit at location 2 with 1, as you can see here, and if this bit is 1, again what we do, we shift the multiplicand by 2. This is because the location of this bit, if this is 1, the location of this bit is 2. So this means now we need to shift this multiplicand 2 times and then add this to the product. And as you can see, if this bit is not 1, we do nothing. We just add zeros, which means we do actually we contribute nothing to the product. Finally, let's compare the final bit of the multiplier with 1, and if this is also 1, now we need to shift it by 3 because the location of this final bit is 3. Right, so once we have done this, now this means after this the whole multiplication process is now complete, right? So what we can do now, we can make a test bench and check whether it is working fine or not. So we have already made this test bench, right? So we can assign 4-bit input to the multiplier. Let's make it 1010, right? And let's save this. Let's run its behavioral check. It's fine. Now let's run the behavioral check for this multiplier. It is also fine. Now let's simulate the behavioral model. This is the result of the multiplication, where this one is the multiplicand 1010, in fact multiplier 1010, and this one is the multiplicand, which is 1011. So these were our inputs, and this is the result. This is the final multiplication result, right? So let's come back to this code. So now once we have implemented this behavioral model of multiplication, we can further optimize this implementation or this Verilog code by using the for statement or for loop, because what we are doing here, we are performing the same operation multiple times. If the number of bits in the input increase, we will be required to write more if statements. So instead of writing this if statement again and again, let's use this for loop. So let's first define this integer. Let's initialize I to be 0, and then let's specify this condition. So in this case, we only have 4 bits in the input, so we specify this condition that I should be less than 4, and then specify this increment statement, and now begin the block of for loop, and so we only need this one if statement, because we can repeat this if statement multiple times using this statement, right? So now let's replace this um, by I and this by I. Depending upon the value of I, it will check whether multiplier, a specific bit of the multiplier is equal to 1. If that bit is equal to 1, then it will shift the multiplicand uh, uh, by I, which is the location of that bit. So if say this bit has this multiplier has 1 at location 2, so this um, I is the value of I is 2, and this multiplicand will be shifted by 2. So now once it is shifted by 2, we add this multiplicand in the product, and then we replace its previous value, which may be 0 initially, and later on it will keep on changing. So we replace this result with uh, the previous value of the product, right? So once this for loop has run maximum number of times, then the product will contain the result of the multiplication, right? So now let's save this, and now let's uh, run its behavioral check. Yes, there are no errors, it's perfectly fine. So now let's select this. In fact, let's do this again. Yeah. So and now let's run the behavioral check of the test bench, and finally now we are ready to simulate. So here we are. So same inputs and same result, but this time we are using this for statement. So this way, once we use this for statement, now we can increase or decrease number of bits in the inputs, and nothing will change in the code. So if we say we have this 8-bit, two 8-bit inputs, then result will be in 16 bits. So now in this case, we only need to change this part where we need to write that I should always be less than 8, because the number of bits in the multiplier or the multiplicand are, in fact, this is directly related to multiplier. So this for loop will run as many times as the number of bits in the multiplier. So this means we run it 8 times, or in fact from 0 to 7, and then this product will have the result. So let's save this, and now go to the test bench. Now again change inputs here, because now this one is not in 3 bits, it is in 7 bits, and the product has 16 bits. So again, let's save this, let's run its behavioral check, let's run the behavioral check of the multiplier, and now let's click on the simulate behavioral model, and now you will see this. So the error or the mistake that we made is this one. So we need to change this to 8, and let's make them an 8-bit input. So let's specify this to be 0, 0, 1, 1, and this to be 0, 1, 0, 1. So now these are two 8-bit numbers. Let's save this, run its behavioral check, and now again run the behavioral check of the module, and then now you're ready to simulate it. So here we are. So this is the result. So this is an 8-bit multiplicand, and this is another 8-bit multiplier, and as you can see, the multiplication result of these two numbers is this one, so which is also given here. So to see the complete result, you just need to expand this window. So here you can see the complete result. So input, the multiplicand, the multiplier, and the product, right?